Hello.
Hello everyone.
Yeah, so we're trying this first episode in English. We want to react directly on what Meta published this week on the tribe model. It's a model that tries to illustrate how the brain reacts to different types of content, and we want to analyze specifically for Meta what it implies and what could be the implication on how we will consume content, but how the content is created to have several effects on the brain.
Yeah. So you went through the study or through what they did,
Yeah.
I guess. So I didn't. I just read a summary of what they did, and today you'll be in charge, and
Sure.
I just try to ask you some questions to clarify some points.
How can I start this? So Tribe is Tribe V2. The model that they released is the second version of a three input model. It has sound, text, and visual content and text. And what happens is that you show these kinds of inputs to a human brain, and then you analyze through fMRI. So fMRI is a functional magnetic resonance imagery. It's a measure of the different levels of oxygen in the blood in the brain.
So the hemodynamic, right?
Yeah, exactly.
Yeah, how much oxygen is transferred to one neuron when an area of the brain is activated by a stimulus.
So yeah, if this is the brain, you can like get info if the one part of the brain is activated, it will have more oxygen flux that is allocated. So you will see like more level of blood and oxygen, and so you can locate that there's activity right there.
Yeah, it's an indirect measure of the activity through the oxygen input.
Yeah.
And maybe you can finish and just explain what's the difference between fMRI and MRI.
No, I don't know the difference. You know?
Okay, it's just for the public. So we do MRI for health check. It's like a picture, and fMRI is a video. That's the functional means it's a video like a long term.
Yeah, and so yeah, why is it important that it's so functional fMRI is functional MRI is that you see the evolution in time of how the content you consume influence how you're going to react. And so first they show videos or just text or just musics to persons, and then they try to see how it and then they analyze how the brains react to that.
So they trying to link stimulus to neuron activation.
Yeah, no, they observe the how the stimulus gives a neural activation.
Okay.
First they just observe,
Okay.
and then they train a model, like three models, Llama for text and two other models for
Like an LLM.
yeah, three transformers
Okay.
models. Well, so LLM for text and other transformer models for voice and imagery.
Yeah.
And then they try to predict how a brain will react to this content when it's just like without showing, like without
without prior knowledge, it's agnostic. Like without prior knowledge, they try to guess which parts of the brain, which area of the brain will be activated through a new stimulus that weren't trained on before.
Well, yeah.
So okay, that's clear. And what do you want to dive next? Like on the model?
I think there's two ways we could dive. There's first like go deeper in what they found on the fact that so they can like predict extremely precisely how an average brain function, and that's very interesting because they did so they first studied 500 brains, and so they had like 500 different types of reactions to the same type of inputs.
Yeah, when you say first, is it in tribe V1 or also in tribe V2?
It's in the first step of the process of Tribe V2
Okay.
when they train the model Tribe on existing data, on
Okay.
like real person on which you show them a type of content, and then you analyze how with fMRI how they reacted, and then so you train the model on this reaction, and they found that the mean reaction of a brain is more like it's easier for the model to predict the mean reaction of the brains than for one brain to predict the mean reaction. Like it's what I was explaining to you yesterday. There's more noise between one specific brain and the average.
Differences maybe, or like the uncertainty between the average brain and someone else's brain is bigger than the uncertainty between their model and the average brain.
Yes.
So they found like the average brain that no one has, which their model is quite close to, but their model is also quite far away from everyone's brain, because everyone's brain is quite different from one person to the other.
Yeah, exactly. And so that's a consequence. So you could, and then you can ask yourself, like, why is Meta doing research in that?
Yeah, that's
Obviously,
a good question.
It's not for just neuroscience. It's because they want to understand how we react to contents we consume, and so maybe that's one of the direction we could go.
So did they talk explicitly about implementing that into Facebook, Instagram, and other? No, for now.
It's just research. But
Okay.
It's so firstly it's more of a AI research paper that's applied to neuroscience, but it has like very important implications on neuroscience, because it's a new way to measure. We never had as accurate measures of how the brain reacts to content, and then there's just how we could imagine they would use this to understand even more how to like create engagement to content we consume.
Yeah, they retro-engineered the brain to know how to feed your feed better, to make you scroll more. Okay, that's interesting. Did you look? I saw they made some voxel model for the output. Do you wanna present that?
Yeah. So voxel, what voxel means is the volumetric pixel. So it's it's a 3D pixel that's modelized.
Kind of like a cube in Minecraft.
Yeah. It's like in a. It's like it's like a cube in Minecraft, whatnot. And so why is this important? Because it helps you, whatever. It helps you you modelize like each part of the brain, and as we said, I think it's also important on a information theory perspective to understand that we cannot with the technology of fMRI, we don't know the content of the brain, of the information that is treated by the brain. This is happening on the neurons level. We only know that there's like blood oxygenation that is happening. So it's more like we know that there's energy that is allocated there, but we don't know the content of how this energy is allocated. It's like if you were like looking at a big computer with like a thermal camera, like that there's energy dissipating there, but you don't know on what exactly it's dissipating.
So during training, you show a face, someone's face. Our brain recognizes it's a face. It activates a special area of the brain. Thus, we associate this area activity with face recognition, and then when we train the model, we expect the voxel of this part of the brain to react the same way when there is a face. Just we expect here to have more oxygen, but we don't know precisely how it works. It's just more oxygen implies more activity.
Yeah.
It's a very broad picture.
Yeah.
And so maybe there is. It's really interesting because it's a finite, discrete approach of the brain, which is a typical approach in engineering. For example, in you talk about thermal engineering. If you take a room, um,
Yeah, please.
if just you take a room with let's say a window over there, it's really poorly drawn. No, let's say we face it like this. Okay, so one way to see that here there is the wall with the window and the sun is coming through there, we can say, hey, the room is roughly 20 degrees Celsius. Or if we need to make a more precise analysis, we say, hey, the sunshine goes through the windows, it radiates through the floor, and thus here this voxel of air, one centimeter square, 1 feet square of space is at this temperature, and it can be associated with, I don't know, 7 a.m. Irradiation. And so it's pretty much the same with the brain, where they took it, they divide it. I think the first one is like 1,000 voxels, like tribe 1.
I don't know. You research?
Yeah, I went through that, and they say like V1 is 1,000, and for V2
it's several
seven.
thousands of thousands. Yeah. You had 7,000 in.
No, I saw like 70,000 voxels.
Yeah, maybe it's something like that. Yeah.
Yeah, so it's to take once again the example of Minecraft. It's like building a brain with cubes, like 70,000 cubes to replicate it, and it's cube that can turn on or off depending on the flow of oxygen.
Mm-hmm.
And yeah, it's a nice breakthrough in neuroscience. So, do you want to say something additional about that?
Yeah, I was trying to find a more like takeaway, like key takeaways for something like more proactive, but that's why I don't know.
Maybe what's interesting is the once again the idea that you can take data. Okay, so we used to learn in school that you learn laws and you apply them, and you already have the solution because you have the laws that are written in books and you just apply them. But this is a really interesting way to learn new laws of nature with science. It is taking like the inputs, taking the outputs completely. Like you just consider that the brain is a black box and it outputs some oxygen level in some voxels, and you try to associate them.
Yeah.
And this is basically the magic of all AI today. Is just you take input, output. You don't care about what's in the middle, and through n of data, the law will emerge, and it's complex law, non-analytical, not completely. But
so yeah, we are curious to see where this is going and heading through.
Yeah.
And probably we will make an update when there will be in this field.
Yeah. So really happy about this new episode in English, and I wish you will like it. Don't forget to comment if you have any ideas if you have any critiques, or if you want us to make an episode about something, we'll be glad to answer you. And
yeah.
see you.
Yeah, see you. Thank you. Bye-bye.